Now it's time for Bruno, to speak about infrared sensors and applied in science and space.
Okay, thanks for the introduction. So I'm going now to talk about science and space use case and have a look at what we've done at Lynred for this type of applications. So first, why using infrared for space applications? Then we will look at what are the detector specifications for science, especially for science and for space. The particular case of infrared for science and what will be the specifications of different example of satellites and the ground space ground telescope, sorry, and what has been our strategy to access these different types of programs. And finally, we like to discuss about the alpha detector that's already talked by Patrick before. So space environment constraints. So space is not good for human. It's not good also for microelectronics because it's very complicated to be there. You have very high difference of temperature between day and night when you are around the Earth, and you have radiations. And radiations is a killing stuff for microelectronics. So you have to be compatible to space environment. You have to have high reliability of the systems and the subsystems also, so from the satellite to the subcomponents. These are in general very long time scales for the development of such programs. We're talking about 3, 5 to 10 or 20 years, perhaps, sometimes. So at detector level, what does it mean? That means that you have to use high TRL technology readiness level to have detectors that are compatible with radiations. So at design level, we need to use tricks to, for example, triple some transistors in the digital domain, and the technology from the foundry also need to be compatible for that. Of course, you have low yield, and when we're talking about millions and billions of detectors for smartphones or car application here, we need only 2 or 3 detectors for a mission because you cannot repair into space and change the detector. So it's just one shot, in fact. For science and space application, you have 2 types of missions. First is what is called direct imaging, which is only you are making an image of something. And then in the space, and the other is the spectrometers. At detector level, you need, as Patrick said, very high performances in terms of sensitivity, in terms of extremely low dark current. We're talking about sometimes 0.1, but 0.01 electron per second per pixel. What does it mean? That means that you can at least count every photon on the detector, infrared photons. And you need also to have a huge field of view to cover, to look at different part of the universe. So science missions in space, you have different types of science missions and different location. As you well know, the Hubble telescope, which is now older telescope in space, very well known. It's Earth orbital. It turns around the Earth. But you have other types of satellites, like the GWST, which is the James Webb Telescope. You probably heard recently with extraordinary images. GWST and Euclid. Euclid is a mission from Europe, from the European Space Agency, that will come in few years. it is located into a region of space which is far away from Earth, in a location which is very stable in terms of mechanical stability. And you can see here the JWST with the big shields that avoided the reflection coming from the sun, to the sun. The third type of mission is the solar system exploration. You've probably heard about the Rosetta mission, which was about the observation and the analysis of a meteorite called Rosetta. There is another mission which is similar to this, is Hayabusa, which is a Japanese mission where Lynred have a one detector inside. Yes, it was it was a success for the Japanese agency. The Japan Space Agency. And on ground-based telescopes, you have current and future telescopes on these slides. First one is the VLT, the Very Large Telescope, which is in Chile, in South America. It is currently under operation. But in the future, you have very big telescope, like the European Extremely Large Telescope, which is 80-meter height, and the primary mirror is 40 meters, so it's huge. We need to have hexagonal individual mirrors that compose this very big mirror and telescopes at the end. And you have in the US other activity like the GMT, the TMT. All of this will be used to analyze far space and to see if we can find some life in exoplanets. Yeah, that's true. So why infrared is interesting for science? Indeed, you increase the analysis of the spectrum. So for the visible, you have only access of a few parts of the spectrum. With infrared, you increase that. You have for the direct imaging, you can see invisible things. For example, this is image coming from Hubble Space Telescope. On the left is visible and the infrared. Here you can see stars that are invisible here due to gas composition behind this. So also for the, I already said that, but for the exoplanet observation, you need to have this spectrometer instruments to analyze the gas composition of the atmosphere of the exoplanet, which is very far from this. It's just like to see a candle very near the sun. In fact, it's so huge. And you can. The goal is to see something like gas, like methane or CO2, and to see if it means that there is life somewhere. Why very large now? Very large detectors. In fact, if you want to observe a very large area in the sky, you need to increase the number of pixels. Here we are talking about 4 million pixels, 2K by 2K. The state of the art now for US competitors is 16, so 4K by 4K. And for telescopes like this one, they need plenty of these detectors, these unit detectors. You need 16 to 64 detectors composed of 2K by 2K. So plenty of pixels. And okay, that's it for that. Yes, so the strategy at Lynred to access this science detector was to first develop the detector itself, which is the alpha detector, 2K pixels, so 2000 by 2000, with a pixel pitch which is 15 micron. It was an ESA funding, and we have the other program, which is H2020, a program which is called Asteroid. And the goal here was to access the technology and to improve, the technology for the larger scale alpha detector manufacturing. And finally, we have this IPCEI fundings for the Nano 2022 to prepare the industrialization of large detectors. These are key figures for these types of detectors. I have already, Patrick also talked about the quantum efficiency, the readout noise, which are under interest and which are very important specification for the detector. On the right side, this is the alpha detector mounted onto packaging close to this electronic board. This has been tested in CEA IRFU in Saclay near Paris in a laboratory capable to do this very fine measurement. We're talking about 40 Kelvin measurement, but they are capable to go down to 4K, if I remember well, but for this detector it's 40. And the performance has been measured, and we are compatible with such very difficult to access performances. So 0.1 electron per second per pixel. An example, and the very first use of our detector, okay, is a program called SVOM in France with French actors, CEA, CPPM, IRAP, and LAM. The goal is to use this detector, this alpha detector, for a mission which is called SVOM, and a camera is called Kagir. So I'm going deeply into this now. So the application is to see events in the sky very far from Earth that are under interest. They are named GRB for gamma ray burst, and this is a phenomenon that appears for a few minutes only. So we need to have two types of detectors. Some detectors are in space, in the satellite, to see very rapidly where is the event, and then the relay is taken by this telescope on ground to observe finally the situation, and this is why we have these two subjects here. In fact, the detector will be located on the ground segment, and I have other images here. It will be in Mexico, in a 1 meter diameter mirror camera, and with the alpha. And we hope to have this integrated in 2024 for 3 years. And we'll see if it's okay. But for the moment, at least, as explained by Patrick, the detector are on the table. And that's it. Thank you for your attention.
We are doing great time-wise, so we have time for a question.
Yes, thank you. I will try and run to you with a little microphone so that you can tell everyone your name and where you're from.
Hi. Hi, I'm Saket, a student from Lund University. Electronics for space is very exciting. I was just curious to know, how do you take into account the effect of radiation on your sensors while designing it, on quantum efficiency, for example? How do you create those conditions, or is it simulation-based?
So the radiation are really related to the readout circuit itself. The detection efficiency, for taking your example, is done by the detection circuit itself, and we are not really, it's not really a problem for the detection circuit, more for the readout circuit. So we have tricks on the design to try to avoid this. And after that, it's a question of validation of the technology of each building blocks compose the detectors. So we have tricks to avoid that.
Thanks.
Thank you for your question. Anything else? Oh, this is Lars Tilly from Nordoms. You already know Lars.
Hi, thank you for a very interesting presentation. Given the very complex technology that you are developing and commercializing, I'm a little bit curious about what's the initiation strategy? How did you start your business and how did you fund it and so on?
In fact, for science is a very small market for space. Main programs are for Earth observation, funded by ESA or CNES in France, the French Space Agency. And also for military application, we have also funded by DGA. But we have customers that are, they know that the price is high for this type of detectors and is higher for space. So there are money for that because they have no choice. In fact, this technology is the only one that can be used in space for the moment, for infrared.
Thank you very much.
Thank you.